I'm so glad to see so many people here, because I think we're going to have a very interesting and unusual discussion about antimatter. Our first guest is an assistant professor at MIT who focuses on answering big questions about the universe by developing novel particle detectors. So please welcome Lindley Winslow. Our next participant is an assistant professor of physics at the University of Massachusetts Amherst, who conducts research in experimental nuclear and particle physics. Please welcome Andrea Pocar. Our final guest this afternoon is also a physics professor at MIT. She's a member of the IceCube experiment, which is located at the South Pole. Please welcome Janet Conrad. All right, thanks so much for being here to talk to all of us. I guess, Janet, maybe you could get us started by telling us how antimatter was discovered and what's so strange about it.
So antimatter was actually discovered in the 1920s, and it wasn't expected at all. At that point in time, they had a pretty nice description of how the world worked. They had certain building blocks, and there was no extra need for any kind of extra particle, particularly one that looks exactly like the matter particle, except that it has opposite electric charge. And so it was a real shock when they actually saw this. They saw this in something which is called a cloud chamber. When a particle goes through them coming from cosmic rays, you can actually see the particles. When the particles go through, you can put on a magnetic field. And if you have a particular kind of charge, say a plus charge, it'll bend in one direction. And if you have a negative charge, it'll bend in the other direction. And so that's what they were seeing when they discovered antimatter. And it was not expected at all.
Yeah. So they immediately, did they immediately know that there was this mystery of why, where is all the antimatter?
It took a long time to actually understand that every particle that we have in our standard model, and we have a lot of particles in the standard model, actually have apparently an antimatter partner. Mm-hmm. Or I think if you think about the standard model and all of the particles in it, at least we are certain that all of the particles that have electric charge have an antimatter partner. There is a special particle that I'm very, very fond of called neutrinos. It's my favorite particle. And neutrinos, the word neutrino means little neutral one. And neutral is a good name for it. It has no electric charge associated with it. And so that's where the mystery of whether neutrinos have a distinct antimatter partner or not actually comes from.
So we know that something caused this. But could you talk about the conditions that this mechanism has to meet in order to favor matter?
Right. We have a very big problem. So if you ask anybody what's their favorite equation out there, it's E equals mc squared. You can ask anybody what their favorite equation is. And that's the one that they will come up with. E equals mc squared tells you that energy can be turned into particles. It turns out that they have to be turned into particles and antiparticles in equal amounts. So if you think about it, if I am producing something that has electric charge out of something that had no electric charge, I had better produce the opposite charge also so that everything will balance out. So that means that whenever we produce particles out of energy, we also get an equal number of the antimatter with it. And that's a big problem if you live in a universe that is clearly only matter. So I like to say that the biggest crime that ever happened is that somebody stole all our antimatter. It's completely gone. And that's a lot to steal. And so we have to think about what it is that can actually make this happen. And so we have to introduce into our theory some kind of a strange behavior among the particles that that will give you a matter-antimatter imbalance. So it tells you that somehow the antiparticles must be behaving differently from the particles. Mm-hmm. And there are not so many places within our standard model where that can actually happen. But it turns out the neutrinos are one of the places mm-hmm. where you could actually fit that in.
So maybe Lindley, could you tell us about, I guess, first about Majorana particles, which the neutrino might be one. So what are Majorana particles, and what do they have to do with this big question that we're trying to answer?
So a Majorana particle is a particle that's its own antiparticle. And so you could figure out that there might be some sort of mechanism where if this is happening, you could make more matter than antimatter. And so as Janet was sort of alluding to, because neutrinos don't have any electric charge, there's nothing really to tell you whether they're their own antiparticle. It's not obvious. And as an experimentalist, it's the not obvious thing that you want to go poke at.
So why is it that if you have a particle that is both a matter and antimatter particle, it's the same thing, then why would that help with our problem where we're actually trying to generate an asymmetry?
So if you have a particle as its own antiparticle, then you could make a process happen where you make more matter than antimatter. So you don't conserve, as Janet said, the matter and the matter in the reaction. You make just a little bit more.
So you need, with most of the particles, most of the cases of the particles in the standard model, you need a particle and an antiparticle to collide, and then that produces energy or something like that, and the whole thing disappears. But if the neutrino is its own antiparticle, then effectively you can have an antineutrino and an antineutrino actually annihilate and disappear. So you can, it's because there isn't any real difference between an antineutrino and a neutrino in this picture.
Right. Or another way of seeing it maybe is if a neutrino comes in produced by some process, in its flight, it transforms into what we call antineutrino and then produces a reaction that produces the matter of the other kind. And so, again, it's a transformation that in that case can occur.
At the very weird thing, neutrinos are being a little bit weird, and we still like to poke at them some more.
That's actually what makes the neutrinos so special.
I think that's why we love them so much. They like to do funny things.
That the rest of the particles are not allowed
right?
to do.
They're constantly doing things
They're very
that
independent.
surprise everyone. Yeah.
Right.
So, so the person who first proposed this idea that neutrinos might be Majorana particles was, in fact, Ettore Majorana, who was a very strange character. Could any of you tell us, maybe Andrea, could you tell us about him?
Yeah, he's a fellow Italian, so maybe I'm
You especially, yeah.
talk about that. So he was Sicilian, and he was a genius since a young age. And he got into Fermi's group in Rome right at the very early age of the nuclear era, when the nucleus was starting to be understood. And apparently there are stories that he showed up in his group, and the very first day he was given what the status of experiments were in the lab in Rome, and mysteries of calculations that couldn't be completed, that were difficult, couldn't match up what the measurements were saying. And apparently he showed up the next day with telling the people there that they had done a good job because everything that they had calculated so far was correct in only one night, apparently. So this is this mixture of legend and reality. But he was, for the few who actually knew him, he was very precocious, very independent. He liked to work alone. And the mystery is that he vanished. Maybe this is a telltale of the things he was studying. In a way,
I'm wondering what evidence we have that the neutrino is a Majorana particle, or how we would find evidence that it is.
So obviously, since we haven't answered this yet, it's pretty hard to answer this question. So the idea that the field is really going after is to look for this rare process called neutrinoless double beta decay. And so the mechanism is that the two electrons get spit out with their two neutrinos. And you can either think of it as what Janet said earlier, that the two neutrinos annihilate because they're Majorana particles, or that because they're Majorana particles, they transform into the other one and kind of get sucked back into the decay. And so if we saw this process of two electrons coming out and no neutrinos, then we've seen evidence that the neutrino is a Majorana particle, and that would be really exciting. Yeah. And there's our Majorana neutrinos.
Yeah, so the little wiggly line is they're coming out.
And there we go.
Yeah.
And so if they're Majorana, you can just complete the line there.
So you see there that now we have two electrons coming out, right? And we have lost the the anti-neutrinos that were coming out with it. The antimatter is not coming out of that decay.
Yeah. So this process made matter and no antimatter. And so that is why we are so excited about it.
And so who figured this out?
It was figured out in the 30s already. The 30s was a time when things moved extremely quickly. From figuring out what a beta decay actually is, to figuring out, well, if that occurs, then we will have the two electron decay as well, with neutrinos coming out. But then if neutrinos might have this property, they might, as we say, annihilate, and maybe this other process exists. It hasn't been found yet, so.
Yeah.
But just to make it very clear, the process on this side has been seen. The process on this side is the one that we are looking for. Because I like to see my neutrinos.
Yeah. So we're actually no neutrinos.
They're the neutrinos, I am the neutrinos.
Oh, I do both.
You do both, that's true.
Just to be safe.
So this process over here only happens on average once every 10 to the 21 years in a typical nucleus. But then this one, how rare is this one over here?
That's at least 10,000 or 100,000 times slower, at least. We only have limits on its occurrence.
And Lindley's holding the record on that limit,
Lindley is holding the record on that.
Currently at 10 to the 26th, but so next week is the big meeting for all of neutrino physics, and I understand that we're about to lose it to another, the third competitor between the one experiment that's not represented on stage.
So what is this record, or how do you?
10 to the 26 years.
So what does that mean that that's a record?
That is, we haven't seen anything, and so we know it has to happen less than one time in 10 to the 26 years.
Okay, in a typical
Yeah.
nucleus, yeah.
So to give you an idea for like how rare this is, the experiments that Andrea and I are building now, we're going to have 1 ton of nuclear material, and we expect 5 decays a year if it is at that 10 to the 26 year half-life.
Okay.
So 5.
And I realized that sounded a little scary. It's actually regular atoms that we put together. It's not nuclear material in the sense of like
Well, it has to
fuel
be
from a
special.
reactor or anything like that. It's special. It's isotopically
Pure.
identified, pure, but it's not dangerous.
And everybody uses a different type of nuclear material, right? Like people have theories like, oh, this one's going to be better for this purpose, or.
Yeah, we argue about that a lot.
And we argue how to use it too.
Yes.
Maybe the same one, but used
Yeah.
in different ways.
So what's the material that each of you?
So Andrea and I both like xenon. I use it in a warm tank of liquid. And with this liquid mix light, when charged particles move through, that's how you'll see those electrons. And then you detect that light with photodetectors. And then you like to use your xenon.
Cold and liquid. In a tank that's made cold and pure. We don't mix it with anything.
So what temperature is XO at?
It's refrigeration, really. It's like minus 100 C or 170 Kelvin, roughly.
So it's not really the liquid nitrogen temperature, but I bet it makes great ice cream anyway. That
Yeah.
would be my
Yeah,
guess.
yeah, yeah. It's
very
enough.
expensive.
But you
great
like
ice
really
cream.
cold as well.
Right. so then some days I like xenon, and other days I like tellurium. And so my other experiment is, the tagline for it's the coldest cubic meter in the known universe. And we will give up the known universe tagline if we discover aliens doing double beta decay research.
With antimatter.
How cold are we talking?
10 millikelvin. So the universe at large is around at 3 Kelvin. So that's outer space. That's not very cold compared to us. We are 100,000 times smaller temperature. So this is the world's most powerful, it's called a dilution refrigerator. It's a very expensive version of the refrigerator you have at home. And so they're 5 by 5 by 5 centimeter crystals of tellurium dioxide. So they are just a little bit cloudy. They're mounted in copper, and the copper is connected to the refrigerator. And so the copper gets cooled down, and then it cools down all of those crystals you see there. So that's 19 towers, 988 crystals.
So something that you have to be very careful with when you're building an experiment like this is to have everything be very, very, very clean, because even the tiniest amount of dirt actually has something in it that's likely to have a radioactive decay, and then that will fool your experiment.
Right.
And so it's not only one of the coldest places in the universe, it's one of the cleanest places. And
When did we first start looking for this decay, and what were those early attempts like? How did we get to the point we're at now?
Well, I would say first you have to discover neutrinos to decide if you're going to look for no neutrinos. So I think that the first thing you had to do is discover the neutrinos, which actually we did through looking for them coming out of the beta decay process that happens inside of reactors. So the first discovery of the family of particles we call neutrinos was actually an antineutrino. And that was discovered in the 1950s.
How do we know it's an antineutrino if we think they might be the same?
Okay, because when these particles interact, they are going to produce, if it is an antiparticle coming in, it's going to produce an antiparticle coming out. And so in comes my anti-electron neutrino, and out comes a positron, which is the anti-electron. And so, so you don't actually know exactly what's coming in. You can't see it because you can't see neutral particles in your detectors. You only see charged particles. But out suddenly, out of nowhere, pops this positron. And you say, aha, I must have had an anti-electron neutrino coming in. Now, the thing is that that's how we've built the theory. We build the theory this way because with all of the other charged particles that we see, it behaves this way. If you have a particle coming in, you have a particle coming out. Antiparticle coming in, antiparticle comes out of these interactions. But we don't know that for sure. But that was the assumption, was that neutrinos and antineutrinos are distinct and that they create these, their partner. So we actually can't tell in these interactions. And the only way I think we'll be able to tell is through this neutrinoless double beta decay instead. But we've seen many cases of both neutrinos and antineutrinos now. In fact, the largest source of neutrinos coming at you are neutrinos coming from the sun. If you could see neutrinos, you could look at the sun. And this is what the sun would look like if you were looking at it in neutrinos. That's actually what the sun looks like in one of our very large neutrino detectors called the Super K detector. But in fact, you can see here that these are pixels, right? You can see each little square. And the actual size of the sun is the size of the little square that's in the middle. So your resolution, your ability to actually resolve something is very poor if you're trying to see things in neutrinos. So it's not really a very good sense to go ahead and develop if you were evolving. So there isn't a lot of need for it. Plus, you also need to become very, very massive in order to be able to see them. So
They don't interact very much.
Yeah, they
Aren't
don't
there,
interact
there's
very
like
often.
billions of them going through each of us every
About
second,
10 billions per square centimeter, or the size
Yeah,
of
the size of
a
your
thumb.
constantly
Per
going
second.
through us.
Going
Right.
through.
And they just don't
Do much.
touch anything. They don't.
Right. They don't interact very often. They're a very independent particle. So that we call it the weak interaction because of the ones that are in our standard model, it is the least likely to actually have an interaction. And so this makes them wonderful particles to study because they can come from a very long distance to you. And then if you get lucky, they'll interact in your detector. But the interactions are so rare that we have to build very, very large detectors, and it needs to be a very large detector to contain their interactions.
Would you describe it? It's such an amazing thing that humans have built the IceCube
Yeah, okay.
detector.
I love this experiment. It's really fun. It's actually at the South Pole. It's right at the South Pole. And we use the Antarctic ice as the interaction mechanism for the neutrinos. So we're looking for neutrinos that are produced in the universe to come through and interact in the ice, and then we'll see the particles that come out of those interactions. So to be able to see the particles that are coming out, we need something that will detect what the particles emit. It turns out that they will emit photons, the particles that are coming out. So we can use these detectors, which are called phototubes, which are absolutely beautiful spherical objects that are a golden color. The golden metal is what's responding to the light. And so we need to drill a hole because we want to put this deep below the Antarctic ice, about 1 kilometer down. And so how do you drill a hole in ice? Anybody know? Hot water. That's exactly right. We just take hot water and we melt our way all the way down in the hole. We put in the detector and we allow it to refreeze around the detector. And it is literally 1 kilometer cubed in size.
So there's one of these in many places.
So there's about 5,000 of these light collection modules over this
and
kilometer.
they form this kind of a cubic array.
And we
Under
look
the-
for neutrinos to come in from outer space and interact in this and produce a big burst of light, which we read out, and from that we can understand all kinds of interesting information about them. But the one thing that we can't tell is if they're a neutrino or an antineutrino. We can tell you what kind of neutrino they are. Neutrinos come in 3 different types within our standard model. And we define what the type of neutrino is based on what it produces in the interaction. So we can tell you if a neutrino came in and produced an electron. We can tell you if it comes in and produces a muon, or we're looking for the case where a neutrino comes in and it produces a tau. But we cannot tell you if that was a anti-electron neutrino or because we don't have a magnetic field. So it would be very, very hard to build a magnet that could cover a kilometer cubed. Yeah.
We have other uses for that magnet. We do it.
Right.
But what's neat, though, is what you can get the handle of is like how important neutrinos are, because they run the gamut from these very, very high energy neutrinos that are more energetic than anything we've ever been able to make on Earth, down to the thermal neutrinos that were made in the Big Bang. And therefore, if you just tweak the properties of neutrino just a little bit, and the biggest one is this Majorana neutrino antineutrino difference, you can really change how the universe formed. And I think that's really what drives all of us here on stage. That's why we love this particle.
Yeah.
It's not unfounded.
And there might be other, besides just the Majorana question, there could be also other neutrinos that we
All
haven't
right, that's my
discovered yet.
favorite question. So the thing about neutrinos is that it's the one part of the standard model where we really see deviations from what we actually expected, from what the theorists were telling us we ought to see. And it is a place where nature is really talking to us instead of us maybe telling nature what to do with our theories, right? And I really like exploring there. And we have seen some hints out of nature that there might be additional neutrinos beyond the 3 that we know of and love so well. But it's very complicated, the picture of what we're seeing in all of our experiments. And so we've been working slowly toward definitive evidence that something is really going on. And one of my experiments, Minnie Boone, just took a really big leap this week. We just put out a new paper that moved us closer. But Natalie had asked me, do I see this as my eureka moment? And the answer is not quite yet. It takes scientists a long time to decide this is really something completely different.
Basically, you saw evidence that maybe there's a sterile neutrino, right? Which is
Right.
so if neutrinos are like ghostly particles, people often describe them as, just with that nickname. The sterile neutrino is a shadow of a ghost.
Right, absolutely. I think ghost is a great description for neutrinos, because how do you know you have a ghost in your house? You know because you look around and there's this debris. The ghost came in and made a mess.
Well, that's why.
Yeah. You thought those were the neutrinos, didn't you? So the same thing happens in our detector. The neutrino comes in and it makes a mess. We don't see the neutrino come in itself, but we see the mess that it makes. So I think ghost is a really good description of it. But the sterile neutrino actually will interact even less often than the standard model neutrinos that we have. And so what happens with them is we have to see them when they play a game with the other neutrinos of neutrino oscillations, causing those neutrinos to disappear and come back again. And so that's where the sterile neutrino comes in. But all of this tells you how rich the field of neutrino physics is, that we have all of these different clues, like they might be Majorana coming from theory, or there might be sterile neutrinos coming from experiment. And so it makes it a really rich place to work. And we actually think that if you put these ideas together, you might be able to get an overall theory that can explain all of these different aspects.
Yeah, that's something that has always struck me, is that we kind of look to neutrinos to solve many of the mysteries that we have questions about.
For being a particle that you are not all that aware of, probably, they're actually a pretty important particle in your life, because, for example, the sun wouldn't shine if we didn't have neutrinos. The very first process that ignites the sun is actually one that involves neutrinos in it. So,
But more importantly, neutrinos are what blow up stars and supernova and make all the elements.
I want the sun to light, not blow up.
And And I measured that, by the way. The neutrinos from the sun.
Yeah.
Oh, okay.
This particular process, in fact, was actually published in 2014.
Oh,
for
tell
the
us
first
about that.
time.
What did you find?
Borexino is the name of the experiment, at the same lab where Cuore is in central Italy. And it's a big sphere of an organic liquid that has a property of producing some light when interactions happen in it, like a neutrino comes in and hits an electron, for example, and that's how we detect these neutrinos from the sun. And it's arguably the one largest radio cleanest volume in the universe. So this experiment was able to measure the neutrinos from the sun at low energy for the first time on event by event. And that allowed us to identify that these belong to this process as opposed to another process in the sun.
And then
It's
you
a whole
can
chain
say-
of processes that emit them.
Yeah.
with
So you
different
can
energy.
say, based on this, okay, now we know how the sun shines.
We know how the
You
sun
can
shines.
say the sun is shining, right? It takes a really long time for the photons that are produced in the center of the sun to make their way out, go down lower in energy and lower in energy till they're visible, and then they finally come to us, 8 minutes across to come to us. But it takes, 10,000 years.
Between 10 and 100,000, depending on who you talk to.
Right, so you never know. Maybe the sun turned off. He
And
can
we have
tell us that it
10,000
didn't.
But
because
we
the
will know
neutrinos
only in
come
100,000 years. So
Yeah.
I think we're fine. At least this room is fine.
straight. But you can tell us that it didn't. It's fine, right?
Yeah.
Yeah, the neutrinos are there.
Yeah.
Right. So we know that we're
That's-
safe for another 100,000
Yeah,
years.
right.
Beyond that, we
Something
don't.
else
No,
will happen.
that's true.
Yeah, I guess getting back a little bit to these experiments that are directly looking for neutrinoless double beta decay. I'm still a bit curious how we figured out even how to do an experiment like this. I mean, what material, you said you prefer xenon. How do we figure out, like, okay, if we get a bunch of xenon together, maybe we can see this? And yeah.
Well, I was telling you a little bit about the type of nuclei that can do this process. And so you can actually then go through, we have tables of isotopes for a variety of reasons, and you can pick out, and there's about 50 candidate isotopes.
Max,
and,
yeah.
Yeah, and then in order to detect something, the higher energy it is, the easier it is. And so we've sort of taken like the 10 highest energy ones, and those are the ones that are would be easy to see. And then you try to figure out how to build a detector with them. And that's really, actually, all three of us on stage are experimental physicists. Our job is to build detectors and answer questions. And that's why actually this field for me is so fun, is that it's like this game of, okay, I have xenon. What can I do with xenon? And xenon's fun because you can actually do every technique with xenon.
I think one of the interesting things about it, though, is that the ideas behind how to do this and how to look for neutrinos double beta decay were actually identified by one of the really great female physicists, Maria Geppert-Meyer. I have an award that's named for her, and she's just was an amazing person. I know she's Lindley's
hero.
Yeah, great guru. So maybe you want to tell a little bit about her.
So as Andrea was saying, sort of the 30s was sort of this time of great jump forward with our understanding of nuclear physics. And she had a preliminary model for how the nucleus worked, and she did the first calculations of this rate to kind of give us the goalpost. And if you ask sort of why it took so long, well, first we didn't know if neutrinos really existed. We had to measure them in the 50s. And then we had this sort of detour where we wanted to see the sunshine. And so in the 60s, we started to try to look for these solar neutrinos. And that turned into a debacle that took 30 years, 40 years.
Well, a great
40
debacle,
years.
I would say. I mean,
It was a great debacle.
It pays for our jobs, I
It
guess.
did.
Yeah, so.
But that simple question of, well, we'll just detect the neutrinos from the sun turned out to be really hard. And that's easy
And
compared.
complicated,
And that's easy compared to double beta decay. And so that's where we are now, is now it's, okay, now we know kind of what to do. Can we do it? And
Yeah, and we've been doing it, not we, I mean, as a community, we've been doing it for about half a century almost now. I think the first experiments were in the either late 60s or early 70s with detectors of the size of a gram or so. And then now we're thinking about tons.
So I guess there was a range of that Mayer calculated. Like it could be this likely or it could be this likely.
Yeah, well, actually, there's a history to that, too. Originally, the first calculation seemed to say that the neutrinoless decay should have been faster than the regular 2-neutrino decay. And then relooking at those calculations, it turned out not to be so. But there was uncertainty into how to calculate these things because it's new physics, and so anytime there's a new process, you put in numbers which are reasonable or minimal extensions of what you know, but you fundamentally don't know, and so you have to at some point look at that. And then you do the biggest, most sensitive experiment you can do in a reasonable time frame, a few years or something, and you look for the process. And if the experiment is too small, it won't see it. And then you go to the next stage because you've learned something and you've learned how to do it better. And that's how the field has progressed.
Mm-hmm. So there is some range, and we've kind of cut through part of the range. We've excluded some range, and now we know that this process is rarer than a certain length of time. Is that kind of how it works? And
Yes.
So how far are we along the scale of
So I would say we've just reached a very exciting point because of this information coming from sort of other types of experiments, we now kind of know where the goalposts are. And so the best limits now are 10 to the 26 years. The next set of experiments is aiming for 10 to the 27 years. And then if we can build an experiment that's sensitive about to 10 to the 28 years and we don't see something, then we know that the neutrinos are not Majorana particles because there's just not much theoretical space left for them to be. And so
Okay,
we're
we
really...
do 100 times better.
We do
than
100
right
times
now.
better.
Yeah.
So that's really kind of a neat place to be. Of course, if Janet's sterile neutrinos exist, we could have even
Changes
more
everything.
fun things in that for us, like it moves things around as to where this decay where we're looking in that.
It would be much more fun.
It would
Also,
be
the
so much fun.
goalposts you talk about are based on this minimal diagram that that has been shown, which is a very reasonable place to go. But on the other hand, neutrinos have surprised us, and so we might actually see the double beta decay with a half-life that doesn't quite match this expectation because the process might actually be more complicated than what was shown on the screen. We're talking about a fundamental process of nature, if it exists, and maybe nature is more complicated than the minimal complication what we're trying to add to explain things.
And so what would it be like if you did discover this? How would it all play out?
Champagne?
Well, I wrote a story about one of these experiments a few years ago that had finished GERDA. Yeah, and they talked about how they blinded the data and then they had an unblinding. So maybe, I don't know if people are aware that that's how it's done, but physicists are so careful that you don't even know that you're going to you're not biased while you're doing the analysis, right? You just do it without even looking at the numbers, and then everyone gets together and then unblinds it. Is that how it happens?
Yeah.
I guess in most cases that's how it happens.
that's
it's a little experiment specific exactly how that is done. But and the pressure is very high on this measurement in particular now. There's a lot of competition, a lot of people trying to do it. And any claim, in fact, there had been in the past a positive claim of having found this decay that turned out to be wrong. And so even more so, I think there's the burden of proof on us if we think we found something new.
Which experiment was that?
It was the GERDA predecessor, but it was a much smaller collaboration, but kind of using this similar technique.
But I think it shows you can go wrong, and his discussion shows you can go wrong in both ways. So for example, there's an experiments that set limits on the 2-neutrino double beta decay that were just not correct, and it's very important to go and explore even those regions that are ruled out, because it turned out that they had made a mistake and missed the signal. That's a really crummy thing to have happen. And it can go the other way also. You can have some kind of an effect in your experiment that is looking a lot like the signal, and it's really important for somebody else to come along and do a different experiment in order to make sure that what you were seeing really is the signal.
So I think this goes to sort of why I work on 2 different experiments and why on the stage you see 3 different experiments, is that in order to really know that we saw the signal, we probably want to see it in 2 different isotopes. So tellurium and xenon, we can share that. And 2 different detector techniques, because it could be a detector artifact, and that has happened in the past, that we've detected things that turned out to be something we didn't understand about the detector.
They're only talking about 5 events, if
Yeah.
they get lucky. And so it's a very tiny number of events. And so, it could be that something's gone wrong. People are a little bit hard on scientists in the sense that when they see something that looks like a signal, scientists can say, oh, well, we have observed this to a certain level, and people are like, have you discovered something or not? And it's really hard for us to say yes for a very long time until there's many, many cross-checks on these things, because it's so easy to go wrong. Experimental physics is a real art.
So if or when you discover this,
When? I'm an optimist.
how big of a deal would it be? I mean, what is this?
This is the last great question of the standard
I think
model.
I think it's really huge, because right now we have no idea what the larger theory is. We have reason to think that there is a larger theory, because we can put together this thing called the standard model that has many particles in it, and we can start arranging them just the same way as you would arrange a periodic table. And we have a lot of history with putting together tables of things and then discovering that there was an underlying theory behind it. Plus, there's stuff that we don't understand, like dark matter, right? But we have no idea what the larger theory is. For many, many years, we pursued supersymmetry, and that just has not turned out to be the right direction, even though it was theoretically very, very promising. So we need something that'll direct us toward what kind of larger theory there is. And neutrinoless double beta decay connects to a very specific class of theories and would allow us to take all those ideas that are out there and really narrow them down.
Yeah, so maybe I know you're all 3 experimentalists, and there's a kind of wall between you and your theorist colleagues, but maybe you could talk about just if this decay is observed, what larger theories that might point to. It would mean that we would have this mechanism for understanding. Yeah, so what is there a name for it? It's not string theory, or yeah.
I guess, let me just make a little intro to this. If neutrinos behave like this, in this funny way of being their own antiparticles, in a way that naturally opens the doors to these objects to exist. I mean, there might be particles out there that also have this feature, no charge, and behave, but which are heavy enough that have never been seen. And in fact, I would say that a majority of theorists, now that doesn't mean that it's the right way to look. Sometimes there's
The vote
a
of
consensus
everybody
that doesn't
necessarily mean
doesn't
it's
mean
right.
that it's more
Yeah.
probable necessarily, but
Yeah,
The only
supersymmetry
vote-
being the good example of that.
supersymmetry being a good example of that. But there's a lot of thinking about whether dark matter, for example, is made of particles which are also of this kind and are maybe linked to processes in physics which are mediated by particles which are too heavy for the LHC, for example, to have discovered. And the other thing is, our current theory lacks to tell us why these neutrinos don't exist. I mean, suppose they don't exist, and neutrinos are just the standard ones that we know. A good theory to me is a theory that explains, predicts, but also tells us whether any of the possible solutions that doesn't violate any fundamental postulate of the theory isn't seen. And neutrinos, based on what we know, should actually behave this way, because you can write terms in the theory that behave exactly like a neutrino that turns into an antiparticle, without really violating any of the fundamental pillars of the theory. And so a theory that has solutions that you kind of say, oh, I just throw these out because they're unimportant, is still an incomplete theory to me.
Yeah, we've made a lot of progress by arguing if it can happen, it will happen. And something has to stop things from happening for us to not see it. And so that's sort of what's behind that particular idea. But one of the things that we think is that at very high energy scales, there is a grand unified theory, a theory that is very simple, and then as you go to lower and lower energies, becomes more and more complicated.
So whatever existed right after the Big Bang, the theory was
Right.
very simple, and then
Right.
as the universe cooled and energies decreased, symmetries broke and things got
And
more
things became
complicated.
very complicated. So people like to describe it as you make a pot of soup and it's all very homogeneous, and then you let it cool and you get globs of stuff in it. And it's kind of that's what's happened, we believe, with our particles. And so there are these grand unified theories that have these Majorana heavy partners in them. And to try to probe at those, we need to look for the light Majorana particles.
And it's also very hard to get rid of them, to write a theory that doesn't have these pop out in many ways. I mean,
Right.
so in that sense, it's very compelling. And the neutrino is the only particle that we know exists that we can directly probe. And so it's a natural place to do it.
So this is always a problem for theorists, because there's a whole set of things out there that it's very hard to get rid of in your theory. One of them is these Majorana particles. Sterile neutrinos are an example of this extra neutrino that I'm looking for. Proton decay is another big one. The fact that we haven't seen protons decay, which is quite good for us because it would be bad if our protons were decaying, but many theories have died on the point that they are predicting proton decay, and it hasn't happened. So we're really at a point where I think we also need to start thinking a little bit more about the way we approach our theories, and whether this, if it can happen, it will happen, is the right way to think about it. I think that at this point, particle physics is really at a turning point, and I think it's a turning point that's going to be really driven by experiment. So sometimes theory drives experiment, and sometimes experiment drives theory, and the healthiest view of the field is when it's going back and forth, rotating back and forth, and I think we're seeing a rotation right now.
So to that point of just that, even though it can happen, this, the particle going whoop and neutrinoless decay, it actually might not happen. So could either of you who are actually searching for this decay, could you talk about what it would mean if this decay doesn't exist and the neutrino is not its own antiparticle? And that's called a Dirac neutrino, right, as opposed to Majorana neutrino. So yeah.
Well, in that case, the neutrino is just like all the other particles of the standard model, which would be disappointing for us, but we still answered a really important question. And then going back to what Janet said, is working on this theory where if it can happen, it does, then we'd have to find a reason why it's not happening. And so that would be then pushing back on our theory friends. Okay, explain to us then what exactly is preventing this from being there.
So if a neutrino and an antineutrino are different particles, then, but they don't have charge, so it seems like they should be the same one. So maybe they have some other property that...
There's some other property. We know particles carry these sort of intrinsic properties. Charge is the easiest one to discuss.
Right, they're sort of like, it's sort of like the DNA of the particle, and charge is one little bit of its DNA, and it can have lots of other aspects of its DNA also.
So then neutrinos would have to have like an extra little chromosome that's preventing them from being Majorana, and you would have to explain it.
But if it's there, we don't know why, and
Yeah.
we have no explanation for that.
And experimentalists are also looking for any magnetic tiny behavior of the neutrino. So far, there's only limits. We haven't found any. But that would be, again, if found, that would be a strong indication of Dirac behavior, because now you have electromagnetic properties of this neutrino. So it's not completely chargeless in the sense of that we think it is so far.
That'll be a really hard experiment to do.
Yeah.
A really hard one, yeah.
Yeah.
So that's the thing, though, about experiment, is you do the easy experiments first, and then what's
Easy
left
ones,
just
right.
gets harder and harder. But yeah,
Well, harder and harder, or brand new.
Brand new. Like you then have no idea what's going to
But it's only by trying
Yeah.
that you'll hit the brand new. I mean, it's not by being idle and not doing anything that you'll hit something.
The brand new is an important point, though. Right now, at least in my area of neutrino physics, one of the things that worries me is I see people proposing larger and larger versions of the detectors that we've worked on for many, many years. And, I worry that at some point it's just not going to be sustainable to build these detectors bigger and bigger, that we have to actually completely rethink our technology and our approaches, and we really need to put some investment into that.
Well, I guess accelerator science has also been going that route, right? I mean, bigger and bigger accelerators, higher and higher energies, but more and more the low energy effects of physics at high energy is being pursued. Also, because practically building bigger machines gets harder. And
In fact, I'm actually working on something related to that. I'm actually working on how to take tiny accelerators, which are called cyclotrons, make them even more powerful than they have been in the past, and then you can bring the accelerator to the experiment instead of having to build the experiment next to the accelerator. And so you can take these existing very large detectors and put an accelerator next to them. And the nice thing about this is that actually this particular accelerator that I'm working on will also be, I think, a really valuable source for medical isotopes too at the same time. So, so you can feel like you can do more than just the basic science with it.
Yeah. And so I was thinking about this earlier, actually, when you talk about that right now the limit is on 10 to the 26 years that this, what is that, by the way? That's like a trillion, 100 trillion years.
I would need a piece of paper to check that.
Yeah, so it doesn't decay
It's
in
100 trillion, let's say.
Yeah, that's
years. But then now you're trying to look to see if it decays in 1,000 trillion years. So you need 10 times more material to do that, right? And then to go one more order of magnitude, you need 100 times more material, where you're studying it, monitoring it for the same amount of time, hoping that one particle in there will undergo this decay. So is it possible to get 100 tons of xenon? I mean, aren't we already kind of at the limit of what we can do?
Possible is probably possible. Certainly technology doesn't scale that easily. And when you scale up an experiment, there is a phase where you gain quickly, but then there's, I think, a second phase where the complexity of the scale-up itself, the engineering complexity of the scale-up, kicks back. And so it's unclear whether, as Janet said, you can just brute force scale up only. I think you have to get smarter as well. And so mitigate the scale up with smart tools or smart techniques that you can implement. And I think we're all trying to think about these possibilities. And there are some ideas there that are being developed still in the proto phase.
Yeah.
So yeah, so sort of building on that, so you guys saw that pretty picture of Core with all those crystals. The next thing we need to do with Core is actually we're going to take crystals that not only are cold, but they also give off light. And so that's actually what that red crystal was about, because it glows if a charged particle goes through it in addition to just heating up. And so that's sort of the things that we're looking at, is how to be smarter about the detectors that we're already building.
Mm-hmm.
Yeah.
So are these experiments running right now? Both of your experiments?
Yeah, I mean, as far as I'm concerned, EXO 200 is running in a salt mine in New Mexico.
Why are they always in these
Just we like
and-
being
Well,
no.
because we don't like easy things. No, the reason is our experiments all have to run underground to shield them from cosmic rays in the atmosphere. And so we use the Earth as a shield, and we have to go roughly a kilometer or so underground. And for X200, at that time, in the United States, that was an available hole in the ground that we could go to. It's in this particular case, unlike the Core example, this is not a laboratory. This is a salt mine where they dispose nuclear contaminated materials from the laboratories that have enriched for the bombs.
Which sounds like a really bad plan for an experiment that needs to be very
It does,
clean.
but the mine is very large, and it's kind of a proof that it's actually done fairly well in a way, because we could run one of the cleanest experiments in the world a kilometer away from a storage of barrels of plutonium contaminated stuff. we're underground, but the actual detector itself is a xenon liquid container, like a bucket, inside a cryostat, which is an instrument that makes it cold. And then it has layers of shielding from radiation that comes from the periphery of the detector. It's been running since late 2010, I would say. We've already published data 3 times. It's scheduled to end in 2018. And we're already into the design phase of a 5-ton follow-up, which is still on paper or silicon, called NXO. And that's going to be a scale-up of what we've learned with X200 with a number of, we think, clever additions or changes that make the scale-up better. But there's going to be, as far as EXO is concerned, the EXO program, a gap of taking data for a while. Our technology and the strength and the risk of the technology is that it goes in steps. There's one detector, you build one detector, you run it, and then if you want a bigger one, you have to build a bigger detector. Quarry, for example, is made of crystals. And so there's technologies like that that could be scaled up more in phases in principle, maybe not Quarry itself specifically, but others. And that really depends on the choice of the technology. In a way, going for the big
What are we
jump.
looking at here, by the way?
Well, this is a container of the X200 experiment. It's made of copper. This is commercial copper, but it's commercially selected copper. Every screw that went into this detector that now is in the picture is empty, but it's instrumented inside and then filled with the liquid, has been screened for radioactivity. So we have to go an excruciating program of monitoring and assaying every material, every component, every cable, every screw that goes in there, because one hot spot, one screw that wasn't cleaned appropriately, there's a fingerprint on it, will swamp the rate of the detector completely. And so that's a big risk, obviously, and sometimes you know only when you put it together and run it. And opening it up to fix it is months of work that you don't want to do. Yeah. So X200 was put underground. It was actually welded in this container, never to be opened again, thankfully, but it was designed to be possibly opened if needed. And it was, in that sense, built very much like a satellite is built. Mm-hmm. You test it, and then you seal it, and you just hope it runs. You hope. You're pretty confident it does, but you're never really sure. It was the turning on of the detector was an interesting phase. So next is going to come next, hopefully. I mean, it's going to be a much more expensive experiment. Mm-hmm. It's a bigger collaboration. We've expanded the collaboration as well. And then on the side, we're thinking also about what after next, so in terms of being more clever. And some of our collaborators are developing brand new techniques to identify the appearance of barium atoms in a xenon 5-ton container. That would be the telltale sign that a double beta decay has occurred. And so they're developing imaging techniques to measure not just a single atom in a matrix, but that one that corresponds to a certain amount of release of energy in the detector, and so on and so forth. That's kind of beyond the next project, but it's possibly ways of being smarter.
So before we go to questions from the audience, I just wanted to ask each of you just to make a prediction, I guess, of when you think this decay is going to be seen. First of all, if you think it's going to be seen, and then kind of what your hunch is about the prospects.
I have a mild optimism that it will be seen. I have to be careful. It goes back to blinding. You look for something because you really think it could be there, and that's for sure. You have to stay honest with the other answer being possible as well. Otherwise, I think that goes down a bad spiral in general. Whether, when, if yes, then when, it's beyond me, but I hope in my lifetime. I really can't make a prediction on that.
So I think I'm going to make a hard prediction. I think we're going to see it in at the end of the next generation of experiments, so 10 years, and it's going to be in a part of the parameter space that no one was expecting to see it.
You just stole mine.
Oh, I did?
Yeah, that was my answer too.
But I don't.
Okay.
But I'm going to let you have the stale neutrinos, and I'm going to say that it's some combination of stale neutrinos and a weird mechanism.
Okay.
Okay. Now you can go.
Yeah, I have the same view. One of the things that happens is that you do these blind analyses and you open the box and you expect one thing, say nothing, or a signal, a specific kind of signal. You open the box and you discover it's not what you expected at all. And I think that's what's going to happen to them. And and I think that will be really fantastic for particle physics. And I also was going to guess 10 years.
And that will guarantee a lot of jobs too.
Yep.
A lot of fun.
Great. Well, I'm sure everybody has some questions they've been racking up.
Trying to understand this, but is there any evidence of the annihilation of the majority of matter? You know, like Penzias and Wilson, they measured the cosmic background radiation from the Big Bang. Is that related to the annihilation of matter and antimatter? Is there any empirical or real evidence of that occurrence?
Well,
When everything annihilated except all the matter that's left. Yeah, do we have any evidence?
I'm afraid that happened so early in our history of our universe that we actually can't look back to that. But I think one of the things that is really interesting about neutrinos is that they actually allow you to look further back in the history of the universe than we can with the photons. So, you know, what happens is that you have a universe that's just full of energy photons, and they're just sort of swimming around. And then finally the universe gets to be big enough where the photons get far enough away from each other that they're not interacting, and then they sort of free stream outwards. And that's the point, that's the last. You can look back to that point, and you can't look any further into what happened in the early universe for these fingerprints. Neutrinos, that happens with very, very early in the universe. And so if we could see the cosmological neutrinos, we could learn an enormous amount. The problem is those neutrinos really don't have very much energy. They're all hanging around right now. You know, there's about a billion of them in every cubic meter of space. But they're not doing very much because they're not very energetic. And so trying to figure out how to find them, that is one of the holy grails of neutrino physics. And there's some ideas out there, but that's.
But yeah, if you thought double beta decay was hard,
try to do
try
that.
that.
But it's a good question, and
Yeah.
if we could get there, we would get there. We would go. Yeah.
All right, well, that's a great place to finish. And let's thank our speakers.